Okay, I'm Eva Silverstein from Stanford, and I want to thank the organizers for this wonderful meeting. It's fantastic to be discussing such confusing issues. It's really the thing we want to be doing. I can report one experimental measurement to do with the firewall, actually. Those of you who know me well know that I use a little tiny device to measure my sleep stages. One can do this for little cost. One can buy a fun little device that will record your 4 stages of sleep on your iPhone. So I do this regularly. It turns out I drink too much coffee and I don't get enough REM sleep normally. But we've been talking about these things for years, but a few weeks ago, Joe and I had a particularly extensive evening discussion about firewalls and AdSCFT and so on. And that night, I can tell you, I registered twice as much REM sleep as usual. So went from like 15% to 27%, which is really good. So it's good for your health. It does cause nightmares, though, evidently. That's a good question. I knew the answer, but the CFT didn't know the answer. So anyway, so I'd like to start. So I was asked basically to overview our approach. This is with Gary and Albion and others such as Steve and Joe and Juan and Don and John McGreevy over the years to understanding the way AdSCFT describes the bulk. In particular, the approach I'll take is sort of complementary to the other ones we've heard. I'll focus on more ultraviolet degrees of freedom, such as D-branes and strings. Part of the reason for that is that the firewall argument, which is really pretty compelling in its own terms, suggests that the problem is UV sensitive. It's an argument that can be made from the bottom up using effective field theory methods, but it suggests this large energy density, which requires a UV completion to assess. So the problem can be phrased from the bottom up, but the solution might come more from the top down. And I think that possibility is at least worth exploring in more detail than has been done. So that's kind of an overall theme, and I'll give you one example that motivates me further, or a few in that regard. Okay, so let me start with a simple observation that has to do with this question of linear operators and distinguishing firewalls from non-firewalls. This is a trivial statement, and I bounced it off quite a number of you, but I just want to say it, lay it out, because I think it's relevant. So let's talk about black holes in AdSCFT. Let's talk about naturally formed ones. And let's also talk about just naturally formed states. Okay, so just all the states of the system that naturally form. So these are identified with the states of the CFT. I'm using the basic axioms of set theory here. I assume I can continue to do that. Okay, so now among these states, however you that comes up. Okay. I'm using what they call the axiom of extensionality, which says that if two sets have the same elements, they're the same set. So, okay. Anyway, okay. So the firewall is also interesting because it's defined by what it's not. It's not the vacuum. Okay, and that could play out in, if they're right that it's there, which is a possibility I'm going to continue to explore. That could play out in many different ways. So I'll take your favorite definition of not the vacuum, be excited above the vacuum by some specific amount, and call those states firewalls. So these are states where the infaller feels drama, however you want to define it. So there's some states that are not the vacuum, and then there are other states, well, that are close enough to the vacuum that we'd say they don't have a firewall. And again, these are all naturally formed states. So among these firewall states, there are ones we already understand. So cases where there's known dynamics behind it, you go in and you shine a laser up the.
Is there a strict definition of unnatural?
I just mean this. You can even use this side to define it if you want. I just mean states that form in the collapse process, as opposed to states that would, if you trace them back, be singular physically and are not excited. That's the whole question. That is the whole question. So the firewall people, Don and Joe and Ahmed and Jamie, suggest that this is a large proportion of the states. I'm being agnostic about it when I write this down. Okay, some of them are, some aren't. It's a dynamical question. So I'm sorry to belabor this, but I just want to. So there might be others, in fact, that involve dynamics that just hasn't been understood yet, and that's basically their contention. So anyway, this is all tautologically true, and because of that, there does exist an operator that is a linear operator in quantum mechanics in the CFT that would take any of these firewall states and project onto it. Yeah, so a non-natural state would be a fictional state in which you have one of these B tilde dagger gravitational waves flying up the right independently of everything else that's going on. We know from their counting argument, the argument that Don gave at the beginning, that doesn't exist. So I don't want to debate that. They've proved it. And so I'm talking about states which may well contain such gravitational radiation going up toward the right, but that radiation comes along with whatever else it is that makes the whole state naturally formed. Okay. So yeah. Well, so some people like to extend the Hilbert space mathematically and mathematically take these natural states and project onto some larger basis, but here I'm just talking about the basis of states that exist in the strongest sense of being formable.
If you have a star, it's collapsing, and it's radiating, and it crosses the horizon, and it keeps radiating. Does that create a fire now? I mean,
no.
Something about shooting radiation out inside.
Okay, good. Let me define what I meant by natural firewall. So I just said, suppose we fix that we're going to have some observer come in and look for what happens to him or her at a certain time. We can certainly send in somebody else who sends a pulse up that they will see, and then then this is an example of what I was just talking about. There's some gravity wave of this B tilde dagger kind in the state, but also there's this I don't know what shooter, the laser operator. But I'm not describing this in a nice compact way, but the rest, when I was saying something else is going along with the gravity wave to make the whole thing natural, in this case it's just the shooter. So what these guys are suggesting is that there's some dynamics that we haven't understood yet, but just because we haven't understood it doesn't mean it. So let me imagine they're right, and there is some dynamics that can do this in other ways than the ways we understand. Then those states still fit into this category, and there's clearly an operator in the CFT that distinguishes firewall states from non-firewall states.
So the way you have this definition, a state that required an initial singularity to form it, would be an example or possibly all examples of the unnatural states?
Well, if it's a physically singular state that therefore isn't in the Hilbert space, it would be unnatural. So I think the answer to your question would be yes. Okay, so this is my brief comment A. And I think what other speakers have been doing is to try to do more, to describe more details about the interior. It's not clear to me how much maybe you can do all of that using only natural states. But in any case, you can do this. And another thing I want to emphasize, which is equally obvious, is that to decide this question of the firewall requires a much cruder measurement than describing every little thing that could happen in the putative interior of the black hole. It's kind of like with normal experimental physics. You don't go for the most subtle signal before you see the leading effects. And because of that, there's also, in my mind, a good chance that AdS-CFT could make this diagnosis, even though the question of describing every detail might be harder than that.
Eva, just to check this,
Yeah.
when you say the FW operator, you don't mean a firewall operator in the sense that some people mean it in terms of a state which is an operator which is 1 on firewall states and 0 on non-firewalls?
Well,
The issue is whether firewall superpositions of firewall states are also firewall states.
To firewalls and non-firewalls.
well, I think we need to understand better what firewall means. I guess I probably could have defined it as just literally the vacuum and everything else, and then it would be orthogonal, I suppose. So let me go on, because I'm okay. Okay, so the next thing I want to do is describe a bit about where this discussion of not the gravitational waves, the D-brane strings, etc., stands. And of course, the two sectors interact, which is important. So let me move to that. Let me start by describing not yet a black hole, but AdS-CFT. So AdS, I'm going to focus on the Poincaré patch, times a sphere is equal, according to AdS-CFT, to the CFT living on Minkowski space. And of course, there's been a lot of discussion of the description of gravitational waves propagating in the bulk. But another, an independent kind of degree of freedom that we also understand fairly well on the gravity side at low energies is D-branes. And we'll also, as I keep saying, be interested in strings for reasons that will become clear. So the dictionary for the gravitational waves, the supergravity modes, is directly related to the single trace operators of the field theory. So if you take a supergravity field and pull it to the boundary, you get these single trace local operators. And if instead you want to describe it in the bulk, you do this propagation into the bulk, and that smears out the operator in the way that people have discussed. So at the boundary, they look like this. In the bulk, they look like some sort of precursor. And there are various proposals for describing that, which we have heard about. And there are other proposals, like what we heard about from Juan, that might be another approach to describing bulk excitations. And what I want to focus on in this part of the talk is a more old-fashioned kind of description of at least some of the physics we know about in the bulk, which is using the matrix degrees of freedom more directly. Okay. So independently of these supergravity fields, so one kind of supergravity field that's interesting, for example, is the KK modes on the sphere. And these are related to chiral operators, trace big phi to the k, where big phi is my n by n scalar field in the super Yang-Mills theory. So those operators are quite distinct from the collective coordinate of a D-brane. I feel like the open string degrees of freedom in the bulk of the space-time are not captured by these. They're independent. And so it's interesting to think about how they are described. They have very interesting properties, such as the fact, as does any bulk excitation, that it commutes with anything at the boundary. And it also has the interesting property of causal restrictions on its motion. So there's some collective coordinate of the D-brane. Let me just call it a scalar field phi. And if I use a metric on the Poincaré patch, which let me just write down to remind you. Takes this form, then the collective coordinate of the D brane phi that I'm talking about is related to this radial Poincaré coordinate in this way, and in terms of field theory units, it is restricted causally that this scalar field move no more quickly than this. Okay, so this is a beautiful thing that the CFT builds up in describing the gravity side. And we can, these do move. Sorry, just a sec. Sorry, what was the question?
That comes from not wanting to spread reading the item on the wrong side.
Yeah, exactly. So it just comes. So okay, thank you for asking that question. So the effective action for so suppose we take n of these D branes, then they have the following properties. The effective action for the center of mass is, as Daniel was just saying, is this, the cancellation here. And the dynamics conspires to prevent the field from moving faster than that. So this is the center of mass. If we take n of them, furthermore, as is familiar from basic D-brane physics, they form their own little supersymmetric SUN n equals 4 gauge theory. So the form of this action is, well, okay, so these are all true facts. Here's another true fact. If you take the n equals 4 super Yang-Mills, as analyzed, for example, by Zeitlin and many others, and you work in a particular gauge, a supersymmetric background field gauge, that is defined in these papers, and you work out the effective action for the first, let's say the 1-1 component of the n by n matrix of scalar fields, integrating out the so-called W fields that connect it to the rest of the matrix, then you obtain the first several terms. I think you obtain at least 3 or 4 terms of this action. In particular, the first correction term, and as I say, several others. And the corrections take a form that makes sense from this point of view. So you take and integrate out these W bosons. You get a factor of n from the fact that there are n of them in loop diagrams in which they run. So for example, this quantity that I just wrote down takes an obvious, takes the form that you expect from doing this procedure. It is a sum of higher dimension operators, functions of phi dot and its powers, suppressed by an energy scale, which is the scale, the mass scale of these W bosons that have been integrated out. This feature would not hold for other tracers of the moduli space, such as the chiral fields. They live at the boundary. They are not subject to a speed limit like this. Yeah.
So just to reiterate this association we've had, phi 1,1 is this matrix is a function of the Poincaré coordinate. It's a function. It's a function.
So it's a
function of the Poincaré spatial coordinate.
At this point, it's a field in the field theory.
Right,
The D-brane coordinate.
And there are
Oh, yeah, sure.
There are paradoxes if you want to directly identify this with the brane position.
No.
Locally in the Poincare coordinate. So at some point you had said that what your picture only works for things that are sort of completely uniform.
No. Okay. Let me come to that. I'm going to include all your arguments. Okay, don't worry. I don't think we disagree. The only things we disagree on are how we anticipate the future playing out in terms of, So the question is, what is this phi? Okay, this phi exists in the theory, in the non-compact Poincare theory, and everything I said is a fact. Okay, this exists. This is also true of phi 1, 1. Some other true. No. Yeah, just look. You can you obtain similar things by including spatial dependence. What you're getting at is these things have to mix with the gravity waves anyway, and maybe there's no better description of those than the one you've given, and maybe that is a limiting factor. But these on their own have a very beautiful candidate here. It's not given by these single trace local operators. It is not given by integrating something in from the boundary. It has to be given by something else. This is a candidate for it. This evidence that I just presented holds for this guy and would not hold for a more naive coordinate on the moduli space like the chiral fields, because those do not have the speed limit. You can usually see you can move those fields as fast as you want, whereas this guy has at least the first few terms in this action that the collective coordinate has, and I think it's a very reasonable conjecture that if you continued this procedure, you would derive the square root form at strong lambda in this field theory.
Eva,
and by the way, just one more thing. This also is a very special thing. We can ask, is there a similar effect that happens at weak lambda in finite n? And at weak lambda and finite n, there's a crossover that's very clear. So these corrections here, which came from integrating out W bosons, at least the first few terms, maybe I should move over to this side, dominate at large lambda. There's a factor of lambda here from this factor of n in this loop. At weak coupling, that factor of lambda is small, and instead, so at lambda small, instead of this, particle production of W's dominates over these effects. And it also has the effect of slowing the field down, but not nearly in this dramatic a way. It doesn't give a sharp speed limit. Okay? So at finite lambda and finite n, as we would expect, these bulk geometric descriptions and causality and so on weaken, and things like the horizon aren't sharp, et cetera. And you see that also in this model. So there are other elements on this list of what I would consider evidence that phi 1, 1 has a chance to be the dual of this phi, such as the fact that in Juan's original paper he showed that this action can be understood as coming from the spontaneous breaking of the conformal invariants, with a few other inputs like the supersymmetric protection of this term. And also, the idea that the matrix degrees of freedom are useful is bolstered by other computations, such as, in fact, some that Joe himself did in matrix theory, showing, for example, that if you use the matrix degrees of freedom to analyze the virialized dynamics of a set of D-branes, you obtain results that are for the size of the distribution of eigenvalues that depends on the whole matrix, but lines up with the geometry on the gravity side. Recently, as Juan keeps reminding me, there's a nice paper of Wiseman which does a similar thing, is able to first integrate out the W bosons and estimate the size of a thermal state in the D0 brane ground state. And in that analysis, he finds an estimate which agrees with the size of the black hole within the D0 brane geometry. So, okay, so that's that. And the last thing I want to say, which comes back to the question Joe just asked, is of course these things interact with each other. So phi and the gravity waves or supergravity modes interact. And so if there's it'd be odd if there were some fundamental limitation on describing the gravity waves. If so, then it would cause problems also for this D-brane once they interact, so that's also clear. But that doesn't argue against this hypothesis, because phi 1,1 also interacts with the rest of the theory at finite n. And the way that it does so could well mirror the way that the collective coordinate interacts with the rest of the theory on this side. And there is the possibility in some circumstances of a more matrix-like description of even the gravity waves. I'm just referring here to the classic open string, closed string duality, where you can describe it in the closed string channel, or you can equivalently describe it in the open string channel. So there are situations where we even know of a more matrix-like description of the gravity waves that are coming in to this picture at finite n. Okay, so oops. Okay, so now let me, let's see. Yeah. Okay, so I think, let me say one more thing that I think Joe was trying to say that I want to include here, which is that, okay, so another consequence of the fact that the collective coordinate phi and the gravity waves interact is that since they showed there's no B tilde dagger excitation, independently of anything else, that's the discussion of these unnatural states from the beginning. There can't, for similar reasons, because they interact, there can't be, independently of everything else, an operator that is just the D-brane position. But there can be, so that is within a certain given black hole. Well, okay, he wants to argue that it's basically, it comes back to the fact that the set of naturally formed states is smaller than the set of states you would get just by independently exciting the probe and the B tilde dagger. So that's more or less your argument, right?
You can imagine your brane scattering process that can produce one of the inside blocking modes. And you get a linear combination of sort of producing it and not producing it.
So that is happening in either black holes, right? So you take a black hole and you send some
You send in a couple of branes where they collide and they can either produce or not produce an inner blocking mode.
Yes, but
so you get a superposition, but the separate two terms in the superposition you don't have in the CFT.
the argument involved is the entropy of black holes is really massive.
Yeah, exactly. That's my.
No, sorry. This argument is.
No,
Sorry.
that was my reaction as well. You can't argue against this.
Sorry. No, I will argue. So let me explain.
Oh, sorry. Yes, you.
This is not so much the count. Let's leave the counting argument as well. Actually, we can use the counting argument in a second, but that's just the experiment is you throw in a pair of D-branes such that they collide behind the horizon. They may or may not produce the inner Hawking mode. So you have a linear combination of two states. In order to sort of have eigenstates, you need that both of those states are independently present in the CFT. Now, if you follow the evolution backwards, shortly before, in order to make those two states, you would need you would need the D-branes coming in, and you would need also the state with the D-branes.
None of that counted
I'm
because
sorry.
you were using the microphone.
Here I've been the microphone police all week, and then I forget myself. So I guess I better put this on the wiki page. So you in order to form these two states, you would need initial states, two branes coming in, and two branes plus the inner Hawking photon coming in. That way you can form the two linear combinations of out states.
But so again, this is a discussion that goes beyond the set of naturally formed states.
And so you would, and arguably, both by counting arguments and blue shift arguments, you don't have that second state with the incoming inner Hawking photon. You cannot form the eigenstates of the D-brane coordinates within the CFT.
In a particular black hole.
So can't I form a family of D-branes that scatter by different angles, or?
You would still need, to get the complete set, you would need the D-branes plus the incoming Hawking modes.
So this is an over-complete set. This is more.
No, it's not over-complete. It's a complete set. It's not. I mean, it's over-complete from the CFT point of view, complete from the point of view of local physics behind the horizon.
Well, wouldn't I need to include the apparatus that will measure this Hawking mode?
Yes.
If you want to make it more complicated, but if you simply want to, because you're making the assertion is whether or not there is in the CFT an operator that projects onto a definite D-brane position. I mean, that doesn't.
So Joe, I've already agreed with your B tilde dagger argument, and with this, I don't think it rules out phi 1 per se, because it also interacts with the duals of gravity waves, and within a given black hole, it could well be true that the only states involve, not just independently phi 1 doing it, whatever it wants independently of what the duals of the gravity waves are doing. Instead, the states that correspond to a given black hole, which I haven't even introduced here yet, so I realize I should do that, the phi 1 could behave in a way that's quite parallel to the way phi behaves in this regard. So let me introduce the black holes.
I have some more general comments to make, but I'm not sure. Maybe I should save them until you finish with your part 1.
Gravity waves, which could also do the same thing, create a linear combination of something inside plus something not inside, which we could do just by scattering, say, gravitons. Why is this not an argument against that? I'm sorry, I just want to understand the argument you gave a little better. Your argument was you could scatter D-branes to create a linear combination of something inside and something that's not outside, but why can't I scatter gravitons to do the same thing?
I mean, I think the same issue comes up with gravitons and branes. I think there's no advantage to branes.
So the question is, the statement is you can't have a graviton operator even outside the black hole?
No, inside, this is inside. Because outside you can do both. Because in some sense, because the scattering process has access to the boundary.
So again, there is an operator in the CFT that distinguishes firewall states from non-firewall states, regardless of any of this.
That's a tautology, but figuring out what it is the question, right?
Yeah, but it's related to this whole discussion of natural versus fictional states. So I think all we need are the excitations of the gravity waves and the collective coordinates of branes that combine into naturally formed states. I don't think we need more than that for. Yes.
Right, just down you said there are some states with firewalls and some without.
Yeah.
I guess the ones without have a regular horizon.
Yeah, just define it with some crossover in energy scale. Just define what you mean by firewall by asking how close you are to the vacuum is your favorite way. Okay, so just make the distinction.
If you're close to the vacuum, what happens to the Hawking pair production process, which is a root cause of all problems? Won't you just keep creating the pairs which lead to the Hawking entanglement problem for such a state if you have one?
If you have a firewall?
No, if you have a non-firewall.
If you need fire and non.
Okay.
If a non-firewall state has a
So I'm sorry. I do not want to get into the let me just say drama state, okay? So that might include what you would consider fuzz. I'm not sure, but I am not. Thank you. I'm really trying to only say things that are true. Okay. So let me move on to more dynamical questions because I think that's really interesting. Let me move on to more dynamical questions.
I'd like to respond to part one. No, I mean, is this part two? Because I'd like to respond to part one before you move on to part two.
I'm going to introduce the black hole, which might help with the discussion of part one.
Oh, this is the topological black hole.
Yeah.
Okay.
Let's talk about that. Okay, so there's a black hole that you get in this way, in the following way, which is so we had the CFT on Minkowski space. It has for patches that have been somewhat discussed already here, Rindler, past and future Milne. And if you restrict your attention to the Milne patch with the standard slicing, and which has hyperbolic spatial slices, and you make them compact, then that corresponds to a black hole on the gravity side, where you can just draw the picture here. So this was the Poincare horizon. A singularity appears on this central time slice. Rewriting the metric quickly. This is what we're talking about. So this is a patch of the original Poincare patch, and let's also focus on naturally formed black holes. So there's no left-hand side, and long story short, this black hole is formed from a shell of D3 branes and evaporates through nucleation of D3 branes. So that's the kind of black hole that we want to understand using these tools. It's particularly nice because it's so closely related to the original Poincare AdS-CFT duality. And causally, both in the CFT and in the gravity side, one only needs to construct data in the Milne patch if all one wants to do is observe things in the Milne patch. So on the CFT side, that's clear. And over here on the gravity side as well, you can get all the naturally formed stuff in this system by starting from the Milne region that I've included here, projected to form a compact hyperbolic space on these slices, which gives me this black hole with a singularity here. Okay, so however the d-brane collective coordinate is manufactured by the field theory, and this whole debate that we just heard was how that is. But what I want to continue with is we know, however it does it, that there is this d-brane collective coordinate phi in the field theory. It, again, has to be possible to construct it using only the Milne patch, the past Milne patch. The question is, what is the dynamics of this black hole? And is it possible to probe it using this collective coordinate? So one approach to that one can take is just use the fact that in the non-compact theory there is this collective coordinate, and then the whole question of what happens in the black hole has to do with what changes when you take the hyperbolic space and make it compact. So because of that, one can, for at least certain purposes, sidestep this whole debate about what the likely dual description is, whether it's simply described in terms of the matrix degrees of freedom or not, and just grant it in the original Poincare and look at what the effect of the compactification is on that. What I want to do is just tell you some interesting scales that appear in this particular kind of black hole, which give me some ideas about the dynamics and motivate some further analysis. So as I mentioned before, the scalar collective coordinate is very closely related. The scalar here I keep talking about is defined by having a canonical kinetic term, and it's related quite directly to this radial coordinate r. And in terms of the field theory variables, we can ask where is the horizon of the black hole. So the horizon of the black hole is at the following scale. In terms of the scalar Vev, this Milne time tau, and the drift coupling lambda. So in particular, just inverting this, remember that phi here was the mass of the W. The Hubble scale of this Milne cosmology is tiny compared to the scale of the W bosons in this problem. So this is where the horizon is, and it is at a place where the field theory, although it lives on a contracting universe, it lives on a very weakly contracting universe and a large hyperboloid at the point where the probe is crossing the horizon. So that in itself makes the idea of a firewall suddenly popping up sound unlikely, but I don't want to jump to that conclusion. In fact, there's something else about the scale that is, so on the one hand, it's a very weak scale, so another way to say it is the SUSY breaking scale inherent in forming this black hole is tiny compared to the W mass scale. There's another way to look at this scale that is more suggestive of some dynamics that might happen, and that's the following. So maybe should I read the wiki or? Okay. So the other aspect of this scale that I want to highlight is the following, and I want to start by talking about a simpler example, another one that actually Gary and I studied a while ago, where we considered, so just I'm going to come back to that momentarily, but there's a simpler example of a compactification of the Poincare theory where you take the CFT on and put it on a circle with supersymmetry breaking boundary conditions. So this theory, so the analogy is basically that this hyperboloid breaks the supersymmetry at the scale of the compactification. And in this other example, what happens is, of course, that this is a confining three-dimensional field theory at low energies. So the upshot for this is that it confines. And on the gravity side, that can be understood in terms of a solution known as the AdS bubble. I think Rob and Gary worked out this solution. And instead of the Poincare slices continuing all the way to the infrared, they smoothly cap off with a circle shrinking in a nice, smooth way. One can make this into a time-dependent problem as well by taking this picture and using it as follows, going out on the Coulomb branch of the gauge theory. The interior of the d-branes that correspond to that is just flat space. And so what one can do with that is make this circle large initially everywhere in the geometry. So it's very stable, at least highly metastable. And then as a function of time, move back to the origin of the Coulomb branch of this theory. And what that does is, on the gravity side, it makes this breaking circle. So as a function of time, there's this SUSY breaking circle, which shrinks as you go toward the infrared, and one can make it happen that at a certain time it shrinks to the string scale. And at that point, there's a known dynamics in which winding strings condense. So in this problem, once this circle shrinks below the string scale, then there are these winding tachyons that form, and they condense. And fortunately, the gauge theory and string theory language for these things are the same. There's a condensation of Wilson lines, which transpires, and that is well understood to cap off this geometry. There are time scales that are important here. So the capping off in this picture happens, as I said, when the circle is stringy. In this picture, let's say that's here, the AdS bubble solution instead is a smooth bubble that caps off with radial scales of order just the AdS radius. And the rate at which that can happen is limited causally. So basically, there's a tachyon or winding condensate phase that appears here, and it propagates out to a radial position corresponding to the confinement scale of this geometry, which in field theory terms, so the energy of confinement in field theory terms is just 1 over the size of the space. So you can use the UVIR relation to match that to a place radially in this geometry. And the dynamics of this time-dependent problem is such that what happens is that eventually the infrared, the very inside of this geometry, is excised because of this condensate of Wilson lines. But it happens slowly. Okay. So the temptation for me when I take the firewall point of view is, could it be that in the black hole case, all that happens again, and causally it would look like it couldn't happen fast enough from this picture. But we're not allowed to take this gravity side seriously because we, after all, there are all sorts of questions about when it might break down. So the question is, when we replace this circle with the compact hyperboloid, could it be that a similar dynamics happens?
Eva, is this a CFT calculation, or is this purely a bulk calculation?
So we need to do it in the CFT. So
not just on the longitudinal field theory of the branes? I mean, you have to do it in the CFT?
You're talking about this calculation?
Well, some of what you're describing seems like it's something that
could just be seen in the dynamics on the brain, the effective field theory on the branes. The question is, do you really need the CFT to do what you're saying, or is this a bulk? This is purely a bulk process you can study in its own right?
Well, so I've described in this problem we have both sides. There aren't the same black hole confusions. I'm just trying to tell you what happens.
Are you doing a bulk calculation or a CFT calculation?
Here, one is, I think the fairer answer is, as usual, the gravity side is the effective side. These calculations of the winding condensate are under control. I am saying that it lines up with what you would expect from field theory dynamics. It lines up with the confinement that we very much expect in quantum field theory. There's your old calculation of Wilson line potentials that develop on short circles. So that's the kind of calculation one would like to do from the field theory side. And all I'm saying is,
well, I mean, if you have a bulk calculation that shows a firewall, you don't really need AdS-CFT.
Yeah, the problem is so that would be certainly true. I'm not saying that I do. What I'm doing here is saying in this problem, we basically understand everything well enough, right? We know the theory should confine. We can use the gravity side to establish this condensation and retraction of the capped off region. And that gives us this endpoint, but it takes a long time. It takes lambda to the 1/4 worth of time. Okay, so that's this example. So in the other example, what we would like to do, I mean, how to say this? I realize it's a little unsatisfying to translate the firewall problem into the problem of proving confinement in a gauge theory. But it's not as far out as some other things that have been discussed here, and I just think it's interesting that might be the question. So the question is, as you say, there are field theory methods that give us some, at least, intuition for how confinement works in situations like this. So there are field theory calculations of Wilson lines. as you say, on the branes, you can do those calculations, and you get a potential which, for example, in this problem, takes the Wilson lines from a ZN symmetric configuration to a confining configuration, and that, there are regimes where you can do that calculation in the field theory. So what I'm trying to say here is that there's a question here, at least in my mind, of whether this happens on the hyperboloid, which corresponds to a real black hole geometry, and if it happens, can it happen fast enough? So there's clearly this unstable regime in configuration space. So the black hole is here in a crude picture of configuration space as a function of this Wilson line, and the question is, could it be that actually that you guys are right, there's a firewall, and that the way it manifests is through Wilson loop condensation on these hyperbolae? So that's a dynamical question. That's a dynamical question that.
See, in some other examples, when you have the confining theory, you don't have a horizon, right?
Yeah, that was particularly true of this case.
So in this case, are you imagining that you have the horizon from the outside, but so what happens? The black hole completely disappears, and we have no black hole.
Yeah. So you're asking what would the endpoint be? Would it be a drama that pokes outside the horizon? Yeah, I mean that would be my best guess for it, indeed, because the kind of Witten bubble solution we know of in simpler situations has that property. But it's an open question. I just think if there is this winding condensate or Wilson line condensate in this gauge theory, and it happens on a time scale that would correspond to reaching the horizon before the whole, before the what do I want to say? It would have to reach the horizon way before it would look like it could causally in this picture. It would have to retract a lot faster than it did in this example. That's the problem.
In this situation, the black hole would not be the minimum of the thermal ensemble, or the stable minimum. It would be some other geometry with.
Right. Right. I mean, here the intuition is that each of the cycles of the Riemann surface is kind of like a Schurz-Schwarz circle, and so from that point of view, for each one of those handles, there's this unstable direction. It is really fascinating what you're getting at, that you start with this Poincare theory, which is just on this moduli space. You do a projection, and the effects of the compactification that I was alluding to before include the fact that, so we work at this level, this mass, black hole mass, for which we just did the projection of the Poincare theory on its Coulomb branch. And whereas that used to be the vacuum of the theory, that used to be the lowest energy configuration, in fact, now there's various other directions you can go in which the energy is negative. Those include the extremal black hole among this class that Ampron studied has negative mu in this sense. But I think separately from that, there's this Wilson line direction, which is also suggesting some lower energy. So I'm personally very curious this is a dynamical question, and it is a question one can phrase in field theory. Of course, it's a strongly coupled field theory, and I'm talking about proving some analog of confinement, which is perhaps out of range of practical theory right now. But if it's obvious to anybody here which way if it's obvious that it couldn't happen, tell me.
No, I'm not going to answer that question. Nothing's obvious in this subject, but the hyperbolic black holes form when all these, we can set it up so that all the sort of circles are much bigger than the string scale when the sort of horizon forms.
Exactly,
so, yeah. Are you imagining that, so now it evolves in, And sort of near the singularity, some of these cycles are going to be coming string scale. And you're imagining the tachyon condensation occurs then, so that it somehow resolves a singularity or replaces it with some tachyon condensate.
Well, so that we had already understood, you and I and John and so on. What I'm trying to do now is make as few assumptions about the gravity side as possible. So because of these confusing aspects of black holes, we don't want to assume the answer. We don't want to assume that there's an inside that works like the naive geometry. But thankfully, we at least know how to name this question in the field theory side. This W could be, instead of winding string, it could be this Wilson line. So that's what I'm trying to do. And it's for that reason that it's not totally obvious to me what the answer is, because if we just use the gravity side causally, it just couldn't retract fast enough. And in our example, it retracted, but it took the usual causal time to do so. But the geometry here maybe can't be trusted, and so I want to ask the question in field theory.
So let me just try a variant of Juan's question. So is it fair to say that the question here is not whether or not is that you have a black hole and whether or not there's a firewall? The question is whether or not you have a black hole or you have something else.
Yeah, so that's I appreciate what you're asking. I just think we need to study the dynamics harder. I don't know the answer, but
Okay, but that could be the question.
Yeah. You could say so. This is kind of reminiscent of what Samir and company do, except to note that this circle is not extra. This is part of the black hole dimensions. So anyway, so the last thing I could mention, I guess I don't have too much time, but another thing I wanted to describe was something very concrete that we can do, which is to generalize. This is to do with string dynamics, partly motivated by these questions, but more generally, I think we have the methods to calculate Bogolubov transformations, generalizing particle production, and also the transformations that people use in this black hole problem to strings using a first quantized description. So I won't really have time to do that given the discussion, but if anyone is interested, I can explain that.
I just wanted to make sure I understood, and this is along the lines of Ed's question. But as far as I understood the second part, you're not talking about any observable that could or could not approach the interior. You're sort of talking about whether I should really be thinking about this as a black hole interior.
Yeah, I'm not assuming that there is an interior. I think, let me put it this way. My own view is either there's some subtle problem with the AMPS argument, and after all, there's an interior. Then in this system, the D-brane collective coordinate, however it's manufactured by the field theory, will have its normal moduli space, which is R6. It will not suddenly end. It'll just do what you would have expected naively in gauge theory. That's one possibility. I'm not assuming that. It's a dynamical question. What I was doing here was just saying, here's at least, as far as I can tell, a direction and configuration space where the system indeed might excise its own interior. And I'm not answering whether it does or doesn't. I'm just saying it's a well-defined dynamical question in this gauge theory. So to me, it's obvious that there are ways this could, since we know so little, there are ways that this could play out where it's very clear that AdSCFT could tell us the answer, at least in certain cases. So there's no blanket statement that AdSCFT is useless.
Right, so it seems like the much harder thing is the converse. It would be easy to see a case where AdSCFT tells you that something happens, but you could imagine to say that nothing happens if everything looks, so far as you can tell, like it's normal, because our statements about the interior always involve the bulk equations of motion. If you're willing to give those up to explain, to have there be firewalls, then you might not be able to tell in that case.
Well,
I agree
okay,
with
so
the
let me,
statement
so
you
I gave you a scenario which would be drama here, and the scenario which I was just alluding to with Tom, which wouldn't give drama, would be an argument like the following. So there's a certain scale of SUSY breaking in this problem. It's non-zero because we put a black hole. We made it compact, and that gave us a black hole and a certain level of SUSY breaking. But it could happen, and in SUSY gauge theory papers, there are some results of this kind, that even at strong coupling, one might be able to bound any drama in the SUSY gauge theory, just any drama, by in some way that depends on the SUSY breaking scale that is input. So there are results by, for example, Mike Dye and Festuccia, et cetera, that maybe Tom as well, I forget all the authors, which for example, give bounds on, superpotentials in terms of F-term, SUSY breaking scales, things like that. There might be some fancy argument that would enable one to just bound any drama for these observables.
in the CFT.
In the CFT. And if it goes in that direction, then these questions that Joe's raising become much more important, because one has to make sure that one is not just looking at some set of observables that is blind to what's really going on. And that's really his concern, I think, if I might speak for you.
Yeah. So just very briefly to summarize, I think it's a very widespread intuition that some kind of matrix variables should fairly directly read off local space-time physics. And so this paper with Lenny and Nick Toomas many years ago, not in this matrix context, we showed that if some fairly simple assumptions about how you read the bulk dynamics could easily be falsified. You could have a bomb go off in the center of AdS space, and something you thought would react to it doesn't react to it because it's the wrong thing. And I do think, as we've discussed some of these same kinds of thought experiments apply to the matrix-type observables. For example, so in particular, the Cabot-Lifshitz-Low approach is not so distinct from this, in that if you throw in a brane from one side, from one part of the boundary, and a graviton from another part of the boundary, when the brane absorbs the boundary, whatever operator is tracing the brane now has a piece proportional to all these precursors we've been talking about. They get mixed together. Moreover, it actually, in these Milne black holes, if you ask how big, so these precursors, remember, are kind of large. They've spread out. And if you ask how big the precursor piece is, once the brane goes behind the horizon, it's bigger than the Milne patch of the CFT, and the precursor is simply no longer present in the CFT. So I think it actually provides a nice example of how the CFT can be blinded to at least some of the interior physics.
Okay. And my answer to that still is, I completely agree with your proof that B tilde dagger does not exist by itself. But it exists as part of naturally formed states, which do have some description. And that's, I think, all that you need. Also, there are examples where you can set up the kind of thing you just said. You have a gravity wave that's absorbed by this brane, and it happens to have come from other branes that we can describe in a matrix language. And in this particular case of a naturally formed firewall excitation from the vacuum, we know of a different description already. So
Right.
I think it's possible one could do better than what you're than Hump's.
Cabot-Lifshitz are deriving an operator identity, and in the case that you're describing, there are actually two pieces. There's the piece for the graviton that forms from the boundary and the one that comes from the brane. And you might say, wow, Cabot-Lifshitz and Low. Wait, let me just finish my sentence.
Sure.
You might say, wow, Cabot-Lifshitz and Low is so ugly. Let's not talk about it. But again, this is what you're led to by thinking about how various thought experiments respond, and I think it reflects the broader message I was trying to make, which is that the CFT really doesn't give you a good description of the bulk for many reasons, and you need an independent theory of the bulk.
So it's all about.
Cabot-Lifshitz Low is ugly even outside the horizon. I mean, the Suvrot said that yesterday, and I can't, right? He said complicate. Okay, you said complicated.
So I mean, there's a sense in which the naturally formed the naturally formed gravity waves all come from the branes, in our case, because they're the things that form the black hole. So they all come from the branes. Now, if you're going to assert that there's not a matrix description of that, I don't see how you've derived that claim, and I think there are limits in which we can see that, in fact, there is such a description. But anyway, I don't need to debate this further. In fact, as you know, we're working on some possible bulk dynamics, which I didn't have time to discuss. But let me just give you a teaser for that briefly, which is kind of fun. I won't give a long lecture about this, but if motivated by the interesting arguments for the firewall, let's say, I, for one, would like to check if there might be some dynamics that's been missed. Again, it's UV sensitive, so maybe we should think about this in string theory. And there is a place where if you ask about the Bogoliubov transformations that come up in the story all the time, so you can do this in ordinary field theory, so for particles, and also I'm saying we can do this for strings. And let's say we take a particle whose mass varies with time, like this. So the frequency is time dependent in this way with some momentum k. And for strings, one can also ask the same question with a time dependence. One can also do this in geometries with time dependence introduced because of the space-time background. So the answer for the Bogoliubov coefficient of particle production in this case is, let me write this bigger. So for the particle case, here's how it behaves. It goes like e to the minus k squared, the momentum scale, divided by basically the rate of change of the frequency. For strings in the same kind of situation, it goes, if I take a circular string, we can calculate this, and the answer is what I've written here. It's exponential in k squared, but there's this size r that appears downstairs, which one can understand from. One can do this calculation in several different ways and reproduce the same answer. And it has to do with the fact that for strings, one can get in a situation where it just doesn't, the result doesn't come from a naive generalization of the particle answer. If you did that, you would get the wrong answer for the strings for reasons that are very clear in this case. The tension can momentarily vary too rapidly for the string spectrum to catch up, and the answer comes out rather differently just for that reason. So, yeah.
I mean, in the string case, you can excite an individual string by gravitational kind of forces, or you can pair create.
This is pair creation.
This is creating strings.
Yeah, what happens is well, here I quoted the result for a circular string. We also tried to fold in oscillations. This is something that Joe and I worked out a while ago and are generalizing to this case, and it appeared in some form in a paper with Centaur and Darriaga where we had a totally different application in mind. But it just occurred to me recently that one can do this calculation. So it seems like maybe these kinds of stringy and brainy dynamical analyses might be useful to do given the general confusion in the subject, just to see if there might be, slightly less subtle resolutions to the problems that involve those UV degrees of freedom. So sorry for going over, let me stop there.
So So the entanglement problem arises because you create pairs out of the vacuum. What do you hope to gain by generalizing this particle production to strings?
Well, the only hope really is that since in this particular case the answer came out rather differently, at least in the sense that it's not, the string answer is not a sum over particle states that you would derive by just looking at the oscillator spectrum of the string in flat space. You get a different answer for a very clear reason. The question is, could it be that in the black hole context, when you do calculations that involve these Bogoliubov transformations between different types of modes,
so you think that you can have some correlations?
Could you get a qualitatively different?
But you mean to get the information out by having strings?
Okay, I'm sorry. I don't mean to evade your question at all. I'm not going to leap to a grand answer to all these questions. My point of view from this is maybe to go a little bit more slowly and study the dynamics in black holes more carefully with a view to this UV sensitivity of all the arguments, but without, I don't have a grand answer or a prejudice. Really, sorry. There've been a lot of proposed solutions, so you can take. There's a menu already.
Sorry, I just missed something about the calculation. Usually when you talk about a Bogoliubov transformation, somehow there's some region or time where the time dependence turns off. So it doesn't look. It looks like it doesn't here. So
no, it does. It does. So there's, when it gets basically as it goes through zero here, it's very non-adiabatic, but that phase is, that time scale is tiny. When this T gets large, it's very high tension again.
Oh, but it looks like there's still time in Hamiltonian, so I'm just not sure exactly how you're defining
so no, this is a standard thing already up here. If you like, there's a good WKB solution for the time-dependent wave functions. Basically, you can look at, the validity of WKB is related to the time derivatives of the frequency in its own units, and this goes to zero at late times. So it's very, very adiabatic most of the time. Just near zero, it's not.
So roughly the positive-negative frequency distinction is conserved?
There's a very definite distinction at away from T equals zero in this example. You have to, when you ask how time dependent is it, you can't. It's this kind of question this kind of quantity that comes in. So, but yeah, we want to do this in the black hole, and we're in the middle of that which I didn't have time to explain.